My name is Arvind. Zin asked me to give a few lectures at this meeting, and she said, I want you to talk about Dataflow. And I said, I don't talk about Dataflow. She said, no, okay, give a retrospective on Dataflow. So this first lecture today is kind of a retrospective, not exhaustive by any means. It relates to some of the things that were happening at MIT in the early days. Also, that is the time from which I have had very strong bond both with Zena and Keshav, because they were both students at that time, and you will see why they're so important. Okay, so let's start with Dataflow model of parallelism. So I think the name that comes up first in this context is Jack Dennis. He had a pretty radical and bold idea, given the time frame we are talking about, that he says, I'm interested in parallel computing, and I want to approach it from a language point of view. He wanted to change the base model for computing, which was sequential set of instructions. And he says, I want a Dataflow graph interface with the hardware. And we'll worry both about the software side as well as the hardware side on how to realize this. And he wrote a very influential tech report, which all of us, were deeply influenced by. And if you look at the history of Dataflow and various projects around the world, and there are quite a few of them, they were all almost directly inspired by Jack's work at that time. I'm not going to be talking much about Dataflow architectures at all today, so I'm not going to survey anything. I'm just interested in giving you an idea behind what was the model in this. So these were the operators that were defined in Jack's paper, the first paper on Dataflow. A very small set of operators. So you have a fork, and you can have any operator, dyadic, or more monadic, etc. You have a switch, which can switch an incoming token either to the true side or the false side, depending upon what kind of Boolean you receive. And then you have a merge operator, which is somewhat more complicated, but in some sense, it's the inverse of a switch. It picks a token either from the true side or from the false side, depending upon the Boolean value it receives on the control input. So if you want to understand it in terms of firing rules, as these things were called, so the firing rule for a fork is simply you take the input token and you duplicate it on both the outgoing arcs. For operators like plus or any other strict function, you can have that thing, and the output value will be the plus of the incoming values on the token. And then switch would be you take the input token, and if it's true, then it will go out on the true link. And in the merge case, if the input token is true, you pick up the token on the false side and push it forward. But notice it's different from all other operators in the sense you leave the token on the false side alone, right? So that token still remains over there. This is kind of important in this case. So these were the four operators, and then we can build Dataflow graphs using this. And easiest way to think about this is if you have two Dataflow graphs and you do juxtaposition of them, then this bigger entity is also a Dataflow graph. Why not? It makes sense. Okay, and the other operator is that if you have, the other construction is if you have a Dataflow graph, if you connect one of the output links to one of the input links, right, like this, then that's also a Dataflow graph, which will obviously have one fewer input link and one fewer output link than that was going out, than that was present in the original G1. And the definition of a Dataflow graph would be that any graph you can build in this manner is a Dataflow graph, given those basic operators. And you can build any graph this way. Okay, so as an exercise, which we won't stop to do, but you should write it down yourself. Assume there is a operator, a graph that does G and another graph that does F. So produce a graph that does the composition, right? So you will have F and G, right, by juxtaposition, and then you will take the output of F and put it in G, which is iteration, and that's how you will get the function composition in this way. This is kind of important from a theoretical point of view, because when you start proving theorems about data flow graphs, then you will often use structural induction. You'll say, oh, the property holds under juxtaposition and iteration, and therefore the property holds for all graphs. Okay, so let's do some programming using data flow graphs. This is as much to illustrate that this programming can be painful, right? So here is a very, very simple operator which takes whatever input value is coming in and produces 2 copies of it at the output, right? So the question is, can we do it using the operators we have so far? So let me introduce another operator, which obviously we can write down. I'm just calling it a gate operator. Right? You can imagine that it lets X go through only if there is a token on C. It doesn't look at the value of C. It doesn't matter whether it's true or false. But something can go through only if both X and C are present. Then it copies X to the output. This can easily be defined using, pluses and so on. All right, so now the question is, given this stuff, can I program this thing? Can I draw a data flow graph that does stream duplication? And here is a graph that does that. And let's analyze it for a second. So this operator over here is the switch operator. And input coming, the token that came on this input is being duplicated. So it will go and sit on the true side, and it will go and sit on the false side. Yes? What is going on here? Is just flipping true, false, but there is a gate. It does that only when there is a token here. Okay, so now you will take this T and it will be duplicated here and here, right? So because it's true, what will happen to this token then? It will go down. What will happen to this token? It will become false, because now there is a token here. It will become false. Now it will, true, which will become false. And then when false comes here, it will consume the token on the false side. Yes? These are fun quizzes, tricks, if you want to, entertain yourself. I can give you more interesting problems, but this is just to show you can write programs this way. And believe me, you can write any program, right? I mean, we already have Turing computability, given these just 4 operators that I showed you. Okay. Some small things are worth thinking about here. So why do I have this gate? Suppose I delete this. I don't have this arc, and I just connect this over here. Does it work correctly?
Whatever the input token gets fed into not, which is semantically unknown?
No, because you have true, right? So true will go here, true will go here. It will become false, right? So you will keep producing an infinite sequence of trues and false. And that means it will keep picking things up alternatively from here. So there is no problem. The answer will still be the same. So why did I draw this more complex graph than the first one, than the one I just described to you? Yeah? Fantastic. Right. I mean, you will have an infinite build-up here, potentially. Right? You can have lots of tokens can collect, and you are providing us some control over it by putting this gate operator. Now you will have only one token in that loop. Yes?
So the problem is not that, which is it? Is that it'll just send out an infinite amount, or that it will keep cycling through on the inside for an infinite?
It'll be internal infinite build-up.
Internal infinite build-up, okay.
Because output is controlled by the input. You have to give me a token before I can produce 2. And I'll produce exactly 2. So I cannot produce more than 2 unless you give me one more input token. So input-output behavior looks fine. And I haven't laid out any rules why it's ruled out, or I should rule out that there should be no infinite build-up. But intuitively you'll say, I don't want this infinite build-up stuff, right? So if you don't, then you have to put in more effort in your data flow graphs so that they still accomplish what you were wanting, but in a bounded fashion. All right. So this is when you are really want to entertain yourself, when you go home, please write a program which is the opposite of that. It'll consume 2 tokens and it outputs 1. Let's just to be more precise, it passes the first one, throws away the second one. So it's throwing away every other token in the input stream. Okay. Now, the values of output tokens are uniquely determined by the value of input tokens. And this is what we meant in those days when we said that behavior is time independent. Now, this is not as trivial a statement as you may think, because imagine a gigantic data flow graph, right? And there are all kinds of operators firing in that. Many of them can happen simultaneously, but even if they were happening one at a time, there is extreme non-determinacy, right? In that, I mean, Keshav was giving you much more sophisticated examples of that. But in data flow graphs, if you're just thinking of an abstract game, you have these graphs, many operators can fire, and you can ask the question, is the final thing that is produced, is it uniquely determined, or does it depend upon the history, or depend upon the order in which operators fired? Because if it does not depend upon the order in which these operators fired, then in some sense this graph represents a function from input to output. Okay, so theorem, a data flow graph formed by repeated juxtaposition and iteration of deterministic data flow operators is deterministic. The proof eluded the MIT group. So there are at least half a dozen papers between 1966 and 73 or something like that, and none of them are satisfactory. I mean, they get into physics of this, and they bring prettiness, you name it. Every trick was tried, but they do not constitute proof in any sense that you and I would agree today is a proof. So even though everybody believed this is true, there was no satisfactory explanation of this, why this is true. All right. So now I enter another name in the picture, Gilles Khan from France. So he published a very thin paper in 1973. It's hardly 4 or 5 pages in the IFEPS proceedings. And he called them Kahnian processes. No, he didn't call them Kahnian processes, concurrent processes or something like that. And the model is extraordinarily simple. He says you have stations with as much power as you want. So you compute with them, and computing stations connected by unbounded FIFO channels. Right? So this is his model. You have a static graph where these things are connected by these channels, and channels are unbounded FIFO queues. Okay, now you can do any computation inside it, but the input-output behavior of the station is as follows, right? You can wait on a channel, block reading from a channel, and whenever you do a send, it's always non-blocking. Why a send on a channel is non-blocking? Because it's unbounded queue. So you can always send something out. Nothing stops you from sending out. But obviously, you cannot proceed if you are trying to do a get, from a channel, and the token is not there, right? So station either blocks for an input on a specific channel or computes. The most important thing here is it's not allowed to say, oops, no token, I will go and look at the other channel. That's crucial, because if you relax that requirement even this much, the whole mathematics will change, right? So the reads are blocking, the get is blocking, but the send is non-blocking. Okay, so this is the example. I think this is taken from his paper, and it's really quite straightforward, so I'm going to walk you through this. So here is some station F, which is getting 2 incoming channels and 1 outgoing channel, and here's G, which is connected to this channel and that channel. And then there are 2 channels initialized by 2 stations, H0 and H1. And let's get H out of the way. All it does is it gets something from the input channel and puts it out. That's all it does. So it does no transformation. It's an identity transformer. It's just that the first thing it puts out is C, right? So first it's sending C to the output. This is the output channel, right? And after that, it just waits for whatever is coming on U, and then it sends out I. If you're thinking in terms of lists or something, this is like a cons operator, right? You have a value that is given to you. You'll put that out, and then everybody's with me, you understand this, right? Okay, now let's focus on this. What is F doing? So F has 2 inputs, U and V, and it has 1 output, W. And a Boolean, it has some internal variable called B, which is initialized to true. And this is an infinite loop here. And what is this loop doing? If B is true, then it waits on U. If it's false, then it waits on V. In other words, it's just constantly switching, because after that, it prints it and sends out whatever it read. So there is really not much computation going on in this graph, right? And what is G doing? It's waiting for U, and if it is true, then it sends out on V, otherwise it sends out on W. Who can tell me the functionality of this network now? So remember, the first thing that will be coming out of here is 0. First thing that is coming out of here is 1. So tell me what sequence will appear here. It will pick up 0, right? It will pick up this 0. It will come here, and the 0 will be sent out here. In the meantime, what is this going to do? It's going to pick up 1 from here. 1 will go here. So this loop is circulating a 1, this loop is circulating a 0, and it's an interleaving, so it's going to produce an infinite sequence of 0, 1, 0, 1, 0, 1. I'm sure there are easier ways to write this program, but we are trying to illustrate something about get and put and all these sends. So the question Gilles Khan asked was, is this process network determinate? Does it always produce the same answer, or does it matter which process executes first? What order these processes executes in? So this is what he suggested. Oh, by the way, I could have easily written that whatever I showed you using JAX operators, right? So this is the F function, this is the G function. etc. You don't have to spend time. But this is just to convince you they're absolutely isomorphic. Anything you can do with data flow graphs, you can write as a Khan process using your favorite language, right? And vice versa. Right, determinacy. A computing station in Carnian network can be viewed as a function from sequences to sequences. So instead of thinking that a token went in and something came out, think of all the history that is going to appear on that arc, right? All the history that is going to appear on the other input arc. And what function is defining is a stream function. It takes those two things and defines the output stream. Okay, a Carnian network can be viewed as a system of recursive equations whose solution characterizes the I/O behavior of the network. All right. And then he went on to say, Kleene fixed point theorem, if each function in the network is monotonic and continuous, then the set of recursive equations has a unique least fixed point. So I'm using lots of big words for most audiences, but you guys are sitting in a functional languages audience. So I expect you to know all these words, right? But I'll define them in a moment. Okay, so let's look at it. So this is my definition of the stream function add. Right? So I have add function which is being fed x followed by x's, y followed by y's, right? And what does it produce? Plus of xy followed by add of x's and y's. Yes? All right. What about true gate? True gate is just half of the switch, right? It passes things when something is true, otherwise it doesn't, right? So you have a bunch of tokens coming in, t followed by b's and x followed by x's. It will produce x followed by, this is the recursion, and if it is false, it just gobbles it up, right? What about merge? So suppose it's true, and I'm saying suppose this is x followed by x's, then it is x merge of b's, x's and y's. Remember, I never looked at y's in this case, because if it is true, then I only look at this. If it is false, I only look at the other side. These are absolutely deterministic. I mean, you can write them in Haskell or language of your choice. Okay, so I could have taken all these kinds of programs, and now I'm powered with this new set of equations, right? Because I have described each operator as a stream operator. So I said, oh, T-gate, it's getting, what is A? Oh, I see, this is A. Okay, and it's getting some input. Over here it produces O, right? And what is A? A is simply the gate of input and B. And what is B? B, because it's initialized with this, B is true followed by not A. These equations make sense? They're recursive? They have to be recursive. If there are loops, there have to be recursive equations. Gilles Khan, monotonicity continuity of operators guarantee a unique solution. So suddenly all of us saw the light. That's what we were trying to do all these years, right? This is how we should have thought about it in the first place. Okay, so now let me just, in one slide, define for you what I just said. So we are working in the domain of sequences here, x1 to xn, etc. The least element would be an empty sequence. You can think of it as bottom of your semantic domain. At that point, the partial order I want is simply the prefix ordering, right? So empty sequence is less than x1, which is less than x1, x2, which is less than, right? Monotonicity, what does that mean? So if I say if x is less than y, then f of x is less than f of y. In other words, in a well-behaved system, if I give a well-behaved operator, if I give more input, what can happen? More output can come out. You're never allowed to retract anything. You go, oops, sorry, by mistake, I sent you 2. Not allowed, right? So once you have launched a missile, it's gone. So that's what monotonicity means in this context. You have stream operators, you give it some input, and more output will come out. It's trivial to show that all the operators that we were drawing are monotonic, right? Continuity is slightly more subtle. And the idea here is, whatever is going to happen after a long time at infinity, we want to get there gradually. So you can't have some funny operator, I don't even know how to write these operators, which think forever and suddenly produce an output, right? So that's not allowed. So you can't think for unbounded amount of time and suddenly produce an output. It's very hard to write non-continuous operator in this domain. And least fixed point now can be calculated just by starting with empty sequences. Imagine all arcs are empty, right? And you just keep applying all the functions one by one to it. And what Kleene theorem tells us is it's guaranteed to be unique wherever you end up. This thing has a limit, unique limit. Okay, so you can work out the details. This is the same program I had shown you earlier. And let's assume initially I input has these 3 values, and A and O are empty, and B has true tokens sitting in it. So if I do one iteration of this by applying, those definitions I gave you. Yep.
You have to include infinite sequences.
Sorry?
You have to include infinite sequences as well, right?
Right. So whichever way you want to describe it, you can write a procedure, which will keep doing the iteration over and over again, right? I'm just doing it for illustrative purposes, right? But if you give me one more input, whatever I have done is fine. I'll just put in one more input and proceed from. Okay? So if you apply the operator for, what was A? I have forgotten. Oh, A was not B. No, what was A? A was just simply whatever B was. Okay, so you get it. So it gets true token because B and this thing. Basically, if you keep doing this, slowly, it'll make progress. And pretty soon, you will reach a point that if the inputs were just 1, 2, and 3, it wouldn't go beyond it. I mean, you would have reached the fixed point of it. If you gave it more input, more output will come out. This is just a theoretical way of understanding that if the operators are monotonic and continuous, we can go from below and climb the hill. We can start out with empty sequences and keep doing it. And there are no surprises, and we will get whatever we compute at that point is the least fixed point of these equations. Okay. So it was obvious to us who were actually trying to write real programs, in those days, try to write, 8 queens program using Dataflow graphs. I think I'll award you a PhD because it's so tedious, right? Reams and reams of paper, spread all over. And, my wife is quite familiar with those days, right? And I relied on, what was that, liquid whiteout or something, right? Because you keep making mistakes, right? So you say, okay, let's leave it. So we were very, very good in writing these gigantic graphs. But it was obvious this is going nowhere, right? If this programming has to become practical, we have to find a more systematic way of doing things. So first thing, to systematize it. By the way, this is also the time when structured programming is coming on the scene. All of you take it for granted, but please remember, Dijkstra's paper, Go-To is Considered Harmful, was published, what, in 1970, is it? Something like that. So not totally accepted that, oh, we can just have, as long as you have conditional schema and loop schema, etc., function calls, you're home, right? So this is the equivalent of that in the Dataflow world. All right, so I will call a graph well-behaved schema if I give it one input on each arc. It produces one output on each arc. Exactly one in, one out, right? So in that sense, all the programs I showed you earlier are not well behaved. Stream duplicator takes one token, produces two, right? All right? Here is a conditional schema. And I claim this conditional schema is also well behaved. So what will happen if you have a token coming in here, right? If this is true, then what will happen to that token? It will be diverted here, right? This is well behaved. So you'll get one token out here. And what token is waiting here? True, right? If while you are doing this, suppose a false token comes, you'll take the next, or it doesn't matter, a true token comes, whatever comes, you will divert it, the input to that side, right? So F and G could all be computing at the same time, right? As long as you have all the inputs, even in this conditional scenario, you know, all those computations could be going on. Yes?
Because that picture has two ins and one out.
Yeah, so for it to be well behaved, you must have a token here and must have a token here. Both must be removed, and a token should be produced here, right, eventually.
Right, but the definition of well behaved is that, what exactly do you mean by one in, one out? Is it not that equal numbers should be going in and out?
No, by one in, one out, I mean exactly one token is being put on each input arc, and exactly one token will be produced on each output arc. How many of you buy that this is well behaved? Yeah? And there is parallelism in it, right? I already showed you that both sides could be going on at the same time. Here's a loop schema, which is also well behaved. In other words, if I give you a token here, eventually one token will come out here. Though internally, you know, this token comes in, I start out with false, it'll keep, as long as this is true, this predicate is true, it'll keep going round and round, right? Eventually it'll become false. And when it becomes false, two things will happen. This token will come out, and now it's ready to receive the next input token. So it's self-initializing, right? We started with some configuration. We put in one token. We'll get one token out. And only when that finishes, then you will go and you can insert the next token in this loop. So as long as this is well behaved, as long as the predicate calculation is well behaved, as long as these things are all one in, one out, then what I'm saying holds, that this scheme will be well behaved. Now this is a much saner way of drawing data flow graphs, because your mind will start working. You say, this is just a block, interconnection of things. This is a conditional schema, this is a loop schema. While P, X gets f of x, right? If P, then f of x or g of x. So we know how to think like that. Believe me, even in those days we knew how to think like that. Okay, so now one thing is, with loop schema has the problem that I pointed out to you earlier, which you can't see in this simple an example, but I have extra slides here. So, you know, in general, it's not just one variable. You can have n variables which are circulating in the loop. And there is a possibility of infinite buildup inside, right? Something can run ahead and, you know, just really cause havoc. So the next schema was a bounded loop schema. So, you know, you wait for it to finish and you say, only then this predicate can accept more. And if you initialize it with k tokens here, then no more than k iterations can go on in parallel. So this is needed for resource management purposes. It doesn't affect anything as far as well-behavedness is concerned. If we want, we can put additional constraint. If you use loop schema, it must be bounded loop schema. Okay, before we go further, it's worth thinking about some simple alternatives. So here is my switch operator. I have A and B. I feed it to F. I also feed it to G. And if it is true, then I take it from here. If it is false, I take it from here. Is this a well-formed schema?
Because 2 points are there.
Well, what will happen here is that if it is true, you take this, and what will happen to these tokens? They will sit there, right? Until the false. So this is not what we wanted. We wanted to throw away those tokens. So this is not a well-behaved schema. It doesn't compose very well. Here is another attempt. So now, okay, so you have convinced me that I need a switch. So I get this, and I'm sending things on different sides. See, this is a lot of work. Why don't I just, this is some funny operator, just merge the two lines. And what's wrong with this?
The output of the second result before the first result.
Precisely, right? Suppose G2x computes much faster than f of x1. Then without the merge, who will come out first? G of x2 will come out before f of x1. Then we already sort of mess it up, right? In this case. I guarantee you, if you did this, it will not be determinate, right? You will lose determinacy instantly. Tokens will come out in wrong order without the merge operator. So even though these schemas are very simple, it's not easy to come up with new schemas, which will have all the desired properties in them. And without the desired properties, they won't compose very well with each other. Okay, so now I want to go one step beyond this, right? So let me show you something about what is called tag token data flow. Consider this situation. So you have true followed by false. You have X sitting here, but we want a token on the true side and there is none. In very colloquial terms, we'll say head of the line blocking, right? Head of the line is true token. It can't move, so everything behind it is blocked too. On the other hand, you're saying, man, I could have executed this false because I have the answer X. I could have, passed it on and more computation can go on. If I could just remember that its position is, that there is something that is supposed to go before that. So if you imagine something like this, imaginary token or a hole or something which is running around. Hard to imagine physically, but okay. So how to model a stream with holes? Well, what I'm trying to say is, suppose you have a stream like this, and we have some things missing in it, we can tag it, right? So we can model it by saying, first element is V1, second element is V2, fourth element is V4. And the moment you start tagging, then it just becomes a set. It's a set of IV pairs. There is no more ordering between them, right? You're just saying this is the tag on it. All right? Let's see if we can write all the definitions we had earlier for this tagged domain that we had, right? So does this first one make sense? Suppose there is a token called IX in X's and IY in Y's. Then I'm saying the output will contain a token with tag I and X plus Y. Yes? Good. It's not asking the question, who has gone before, who is coming afterwards, right? Just, this makes sense. What about true gate? A bit tricky, right? Because how do I know the position of something in the output? Input is easy. Take the I thing here, I thing here. But how your position in the output sequence determined? It depends on how many true tokens were supposed to be before I. In other words, if I can look at this input stream of booleans and up to point I say, please tell me, how many tokens, true tokens are there, whose index is less than or equal to I. If that value is k, then the answer to this question has to be that the output will be, you will be putting IX into the output stream, depending upon the value of the Boolean stream. It's tedious to read this. I hope everybody gets the idea in this, right? You have a sequence of tokens coming in, sequence of tokens coming in. These sequences have to be the same size. So I have a true token here and a value here. So what do I want to do? I want to pass it on. If it's a false token, what do I want to do? I have to gobble it up. The problem is, when I put it out, I have to attach a tag to it. To attach a tag, I need to know how many true tokens came before. Right? That's all it's doing. And you can play a similar game with the merge operator, because you have to know whether to pick from this side or pick from that side. Right? Yep. That's a very good question. So just read it as a mathematical definition. It'll be a very big pain to implement this. Right? So that's coming too, right? At least from theoretical point of view, it's coming. Because obviously this involves some kind of sequentiality, right? Because I have to keep track of all the tokens that are coming in, so the operator has to have some internal state. It's not something I really want, right? In this case. Okay, but that's the idea on the merge operator also, because it has to keep track of whether it's picking from this side or that side. That depends upon the number of true tokens that have been received in order to pick up the right tag. Now what I'm going to do is introduce a new operator called D. Wherever you had an initial token in your graph, I'm going to put this operator, D. Right? And what this does is, it just increases the tag by 1. So the first token that comes out has the value A, because this operator is parameterized by A. And after that, whatever comes in on the ith token, ith tag, I put it out in the tag I plus 1. This is like saying, if you have a loop, right, and it's going to have some initialization in it. So first token, if you numbered it 1, the next one will be 2, 3, 4, right? So what is the easiest way? Anytime you had an initial token, just put the D operator in there. Okay. I can play the same game again that I was playing before. So I can say, I'm defining a new domain, stream with holes, right? Which is just simply this tag value pair. The least element of this is again an empty set. A partial order is a subset order. This thing is less than that if anything that is present here is present in the other one with the same value. And if you could show the definitions I wrote on the previous slide are all monotonic and continuous, then what does it tell you? That the network of tagged operator is also deterministic. Right? So that's just a mathematical point I'm making. We had a stream sequences, right? And we showed that, if you build such a network, it will be all deterministic. And now I'm saying, suppose we have tagging, and I gave you some rules for tagging, then the tagged sequences, that data flow graph is still deterministic. Now, why we are interested in this is because it has more proof, more parallelism. Because remember, I showed you these slides by starting with head of the line blocking. That is gone now. I don't have to know that there is no token on the X line. I can still go and compute from the Y side. So theorem suppose the least fixed point of a data flow program under FIFO interpretation is X and under tagged interpretation is Y, then it's guaranteed that Y is greater than X. Which is like saying you can see more, you can compute more. There's more parallelism here. And this is what we did, Goslow and myself, proof of this in we gave the interpreter and showed that indeed it's deterministic. But the whole motivation was to exploit even more parallelism in data flow graphs. So this is often called the tagged interpretation, of data flow graphs. Okay, now I want to show you it had some impact on the schemas. Because we believe in these well-behaved schemas. So now I've changed the definition of one in, one out. So what is this? What is it saying? If all the input tokens have tag C, right? All the output tokens have tag C. Then we say it's well-behaved. That's the new version of one in, one out property. Okay? Self-cleaning. Initially, the graph contains no tokens. When all the output tokens have been produced, no tokens remain in the graph. Because remember, I'm replacing all the initial tokens with those D operators in my scheme. All right? Now let's understand the consequences of tagging. Now this schema suddenly starts making sense. I can actually simplify even the switches. So suppose this has tag I and this has tag, the only way they can match is if both of them have tag I. Just put it on the true side, put it on the false side. So a tag either goes to the true side or goes to the false side. So what will happen when you merge the two sequences? They were disjoint tags, right? Either a tag went this side or it went that side. So when you merge it, everything remains fine. So you can prove that even this conditional schema in the tagged interpretation is deterministic, has the right property, one in, one out. Even if fx1 completes after gx2, the output token will carry the correct tag, which is what we are relying on, as opposed to the exact sequence, order in which things come out. Tagging simplifies well-behaved schemas, increases parallelism at the cost of increased complexity in implementation. Where is this increased complexity coming from? You have tags, right? So previously you could just say, it's an order, you don't have to remember. Now you have to tag, and tags are not infinite, so you have to do management of tag space. You have to reuse tags, etc. So this is the world of pure data flow graphs in this. And you can write interesting programs. But when you have to deal with data structures, some problems emerge immediately. So suppose we want to add two arrays element by element. So what will happen is, if you're thinking in terms of pure data flow graphs, you say option 1, the whole array is carried by a token. I have a gigantic operator, right? Nobody told me. I mean, Khan said any computing station will do. So write, a big fat add operator. So this is not very practical, because how big a token do you want to carry? Because we were also thinking hardware. We are actually eventually going to build all this stuff. Option 2. This has a lot of appeal. So you're saying, oh, why don't I just think of this array as a sequence of tokens? So how do we actually go from that to this? That we can debate, right? But it's conceivable in some situations you can just think of that array as a sequence of tokens flowing along an arc, right? Option 3, instead of dividing it temporally, you can divide it spatially. You can have n operators, right? So the first elements of the arrays are being sent here, the second element sent, etc. And of course, you can have any combination of 2 and 3. The point is that such a choice of representation has to be made by the user or the compiler. I mean, this is way above whatever we were doing in the data flow graph level, So immediately practical questions will come up. How did you express your array computation? How should I, compile it into a data flow graph, etc. These options are not suitable for handling complex or sparse data structures. So if the algorithm is very, very simple, right, signal processing, something highly dense, maybe you can have enough oomph to sit down and translate everything into either spatial or, the sequence of token kind of parallelism and exploit it that way. Okay, so what do I mean by a general model? So the model that we zeroed in on, that is still probably the most common model of parallelism, is what we'll call parallel multi-threaded language model. So the idea here is you have some function f which invokes g and h, and g may invoke some loop, and there is parallelism at all levels, because in data flow way of thinking, while f is happening, it spawns off g and h. They can all be going on concurrently, not just these two, but even f could be going on. There may be more activity going on. That's what I'm trying to show by these threads, that there could be multiple threads at any level in this, and any part of this activation tree could be active, right? So this idea is this can be expressed in data flow terms. You will need some extensions, but this is by itself is not a problem. In fact, data flow will support this model very well. The problem is modern computing doesn't look like this. It's also have the heap of shared objects. So I may allocate something and somebody else may modify. I may allocate something and pass it backwards, right? So the object lifetime is not necessarily associated with the lifetime of the activation frame. And this is needed to support just about any modern high-level language, this kind of a structure in this. And then there is the added problem in any such model of what do we mean when we access shared heap objects, which all of you who have tried to write multi-threaded programs are very aware of it, that a read comes from somewhere and a write comes from somewhere. What happens if the read shows up before write? So any time you deal with shared objects on heaps which are being accessed by concurrent data structures, you have to worry about synchronization. You can put in, locks, synchronization of your choice, but something more has to be done than just the simple picture I'm showing you in this. But otherwise, a very powerful model. And what we convinced ourselves was that pure data flow systems of the form I have shown you so far it's too much. I mean, it will be trying to, it just doesn't fit. It doesn't have enough expressive power to do this kind of stuff. So we had to do something else, right? We had to extend the model in some non-trivial way if we want to express general purpose computing models. Now remember, the thing that is not coming through in this talk is we are always trying to build hardware to support these things on one hand. We are always trying to write programs at some high level notation which can be translated so that it will run on our machine. So we were falling on both counts. From hardware side, we are seeing lots of problems. We can't carry big tokens, right? We can't do arbitrary computation on these nodes. And on the software side, heroic compiling doesn't quite make it. I mean, this is super heroic compiling you will have to do if you want to go down to pure data flow models. Okay, so in some sense, the project at MIT, from 79 to 94 was motivated by, because most of this stuff about tagging, etc., and some dealing with some data objects in some simple way, this was all known even before I joined the faculty at MIT. So it was the work that happened at MIT when Keshav and Zena were there is all about supporting this sort of dynamic data flow architectures and the languages that went with it. So first thing we have to realize is that if we think in terms of a shared memory system, we have a memory and we have processors hanging off it. Data structures reside in memory and tokens only carry pointers to them. That's the only practical solution, right? So you leave heavy things somewhere and you remember the address. I left it there, and now in your data flow graphs, these pointers are flowing about. And then we introduce the idea of I structures. The idea of I structures was that these will be write once data structures. So you can allocate some location, you can write it once, you can read it as many times as you want, and then you deallocate it. You can only write it once. Yes? So you can't do it using I structures. Maybe the algorithm will be impossible to express, in this or something else, right? Okay, I structures are like variables in logic languages in the following sense, and Keshav was the one who pointed this out, that in logic variables, you start out with something which is undefined. And as you unify, it gets more and more defined, right? So here it's a very simple form of logic variables. It starts out undefined, and then it gets defined once, right? Because we are not storing anything other than scalar values inside these things. Okay, and these things, many, many years later, got incorporated in Haskell in form of I-vars and M-vars, etc. Now, what is interesting is what we were thinking in terms of hardware. So at the hardware level, there is going to be an I-fetch instruction, which is just like a read, go and read it. And at the other instruction is store. You give me a value, address and the value, and you go and store it. There, the difference is, because it's write once, no problem if the reader arrives before the writer at the memory location. Because the reader will just have to wait. He says, sorry, I came too early, nobody home. So it just waits, until somebody writes. And when it writes, everybody who was waiting suddenly says, now I have the answer. Right? So that's the kind of storage we talked about at that time. So there was going to be this storage, right, which has two tag bits, which either indicates that there is nothing in there, or it indicates that the value is there, or it indicates that somebody is waiting, right? the reader came before. So that's what this green-red flag is. So when you have iFetch, and this is the thing that takes a little bit of, from hardware point of view, you have to figure it out, that it's not a primitive operator like plus anymore. iFetch is a split phase operator. So when you get something here, what is the address you have here? Address just tells you where you can find the value. So in the background, a request is being sent to the iStructure store. Please tell me the value of this location. And whenever you have the value, please forward it to this operator. And remember, we are living in the tagged world. So what I'm doing is I'm, first of all, going somewhere in the memory, and I'm sending a forwarding address, which itself is a tag in this. So does everybody see that in this system, if readers arrive before writers, there is no problem? They will just wait at the storage. And if you want to get into the details, which I won't just now, you need to deal with multiple deferred reads. It's actually quite, there are elegant ways of dealing with that problem. And you may want to provide additional operations because you may want to allow sequence of writes. So, readers and writers are matched one-to-one, and M structures are a little bit like that. Okay, so the whole idea was that we have a high-level language, and we'll compile it into Dataflow graphs plus iStructures, and then we are building hardware on which these things will execute very efficiently. So this is our love affair with functional languages. So Backus was already saying we should do functional, and it took us a few years to realize that when we talked about Dataflow languages, really they were like functional languages. So then we got into serious study of functional languages at that point, and then we made some extensions to functional languages because they did not deal with iStructure-like notations very well. In this, and a lot of hardware was built. I mean, this was really a gigantic project. We were working in collaboration with Motorola, and we built two 16-node machines. One was at MIT, and the other one was sent to Lawrence Livermore National Lab. And we built small machines, also 2-node machines to experiment with. And it was proudly displayed at the supercomputing in '91. Motorola had a huge booth and a mock-up of the machine because we couldn't transport the machine at that point. But it was running programs at MIT. So this is a picture of where some people are there. I wonder if you can recognize anybody there. Who's this? Zena is hiding in there. So there are lots of interesting people. You may not know them. They have gone on to do bigger and better things since then. And there were lots of people involved on the software side. Right, so I've shown just some pictures. So there is Nikhil and Keshav and David Color. Greg was doing mostly hardware stuff. Ken Traub was a super guy, unfortunately died last year prematurely. Jamie Hicks still around, Derek Chu, Steve Heller, and many, many others. And you see. Okay, so now let me do an assessment because I don't want to talk about Dataflow architectures. So this is just a very high-level view of what I can say in a few minutes about this. They're used extensively in modern microprocessors. But you wouldn't know that unless you are really an architect yourself, right? So you have to really get inside. Why? Because the interface with microprocessor remains totally sequential. We follow exactly the same semantics for instructions that we followed in 60s, right? You have a sequence of instructions, and that's what you offer to the processor. And then it does magically something. It exploits parallelism in that sequence. which we couldn't imagine in our days, right? And so interface remains the same, but internally, how it gets the parallelism, I'll tell you in a second, but it executes it absolutely in Dataflow style. It executes an instruction whenever its operands are available. Okay, it builds reorder buffers and so on. Now, the way modern processors do it is by what I call extreme speculation. Extreme speculation, right? So just to exploit pipeline parallelism, I still have to know who's coming behind me. And I can't know that, until I have executed the instruction. So I said, oh, I know it's PC plus 4. Or whatever, I get into very sophisticated predictions. And I said, no, it's such and such. If you go to other speculation that goes on inside the machine, it's just remarkable, right? We predict all the addresses. You say, okay, so I have to do this read, but it's conceivable that write in front of me may be writing to this address. Let's speculate. Because most time it doesn't write in the same place, right? So there is a whole way of thinking about speculation which was totally absent from our thinking. It was not part of the Dataflow scene. Because for us, parallelism was never an issue. We had parallelism coming out of everywhere, right? We could take algorithms and, parallelize it if you wrote it our way. I mean, not every algorithm, because there are algorithms which don't have parallelism, but much more than, you couldn't blame lack of parallelism. That's why people couldn't do it, right? I mean, there was parallelism, we still couldn't exploit it, right? That was the issue in those days. So this is something worth thinking about, because this theme will keep happening over and over again. What is the role of speculation in computation? Now, compilers extract parallelism from sequential codes with varying degree of success. Oh, by the way, I want to tell you, in most advanced microprocessors, you can even do the following. You have a long chain, right, of instructions that you have to execute, which you may have already speculated, right? You have speculated all the jumps, and then you say, let's cut it wherever we want, and we'll execute each strand in parallel. So, but what happens if this data depends? Okay, then we'll fail, right? So you get into this very sophisticated ways of, looking way ahead and cutting, and in case of speculation failure, you will do something, with it. Okay, so compilers. So that's why our interaction with David Cook was so strong starting out, because they were sort of the champions. They were leading the charge. I mean, them and some people in IBM under John Cock and Van Allen, etc., data flow analysis. So this was it was pretty young discipline at that time in late 70s, early 80s. Okay, how to extract parallelism from sequential codes. First, people were trying to do this because they just wanted a better schedule in hardware. But then Cook and company pushed it because they were trying to exploit vector machines, where you needed much more parallelism than what you can see, ordinarily in this. And I don't have to tell you that this is with varying degrees of success. I mean, Keshav will say that if you stick to dense codes, it's pretty much a solved problem now, with polyhedral analysis, etc. People can do all kinds of things, So if all your examples are going to be about such dense codes, compiler technology has caught up, with it. Parallel programming remains difficult. Most users have little interest in rewriting their program to exploit parallelism. Now, you have to understand this comment from where I'm coming. I don't know how many talks I gave in 80s, all over the world, saying all programming is going to be parallel in 10 years. I said by 1990, everybody will be writing parallel programs. We'll be teaching nothing but parallel programming to freshmen at MIT. Sequential programming will be taught as a special case of parallel programming. I could not have been more wrong. Okay, I was right only about one thing. All machines did become parallel. I was off by 10 years, by 2000, they were all parallel. But programming-wise, I was shocked. I still am. That how tough parallel programming has turned out to be. The other thing is, psychologically, I didn't get it right. People have no interest in running their programs in parallel. Some do, right? But the number of people who are interested in that, believe, is very tiny as compared to the rest of the world. As long as they can get their answers, they're happy. And if they have a choice between rewriting their program or buying an expensive machine, they'll go and buy an expensive machine. Or they'll come and rent yours, right? So I think this view, average programmer views exploiting parallelism in their program. By that I mean so that they have to suffer the pain of it at the same level as saying, I wish my clock was faster in my microprocessor. Well, that's not my problem, Intel, right? It's completely somebody else's problem. So I think this combination of two things, that the parallel programming turned out to be very hard for performance, right? There are many situations where you have to deal with concurrency issues. I'm not talking about that. I'm talking about parallelism for performance. The number of people who are interested in this is negligible, okay? And so it remains a domain of experts. Then the second thing that has come as a shock to me is when you go around companies and seeing what kind of multi-threaded programming is being done. Everybody has told me, we are told day and night, write data race-free programs. And since nobody has a language that can guarantee that, here is a slew of tools, right? Make sure your program, at least according to these tools, says there is no data race in your program. And as long as it passes that, then you say, I don't know what's going on. This is too tough. But people do not go beyond this, right? So they're writing some annotations, some very, very high-level multi-threaded stuff. They're relying on tools, etc. So ethos is somebody else's problem. And in spite of all this, most microprocessors are multi-cores. Most systems have many concurrent processes. I'm always fascinated when I'm sitting on my, laptop or anything. You touch the keyboard, 10 more processes start. What did I do, right? So it's just, who knows where these processes come from? But systems are so highly multi-threaded. Obviously, it's not for performance, right? There's concurrent things going on. It's much easier to think of many problems in operating system as if they were independent problems. Sometimes they collide with each other. Okay, so put in synchronization for that. That's what Linux kernel hackers do, right? That's what some other, sophisticated operating systems programmers do. But applications programmer, very little of any of that. I think because of all these things, really there is a move now towards very, very domain-specific solutions. So we regard general problem as very tough. Some people still want performance. Say, what is your problem? What program do you want to run fast, right? And literally this is how it works today. You will take top 10 programs, top 10 not because importance is always judged in terms of money, right? I mean, how important these programs are. And then you would employ enough people until each of those runs faster, so that average person is not affected. So whenever you take some complex programs and run it in a multi-threaded fashion, so Keshav called them what? Stephanies of the world. So you hire Stephanies at that point, right? As opposed to hiring Joes, right? Because Joes know nothing about programming. Nothing about concurrent programming. Okay. All right. Sorry? All right. So I want to say a few more words. So one is coarse grain versus fine grain data flow, because you will hear this word often. People say glibly, oh, the mistake was to exploit parallelism at such fine grain level. Okay, maybe there is some truth to it, but I don't think people understand what they're talking about when they say that. But let's see what is the reality of it. Dataflow model says nothing about the size of tokens or the complexity of computing nodes, right? In practice, the cost of implementing fine-grained asynchronous parallelism, the operative word here is asynchronous parallelism, right, is high. So many systems use data flow ideas at a macro level, and at low level they say, but I know the timing, so I don't need these unbounded FIFO queues or your fancy tagging, right, because I know when it's going to be done. So there are very, very few instances, where you have to assign tags because you really have to wait, for things. And if you look at it from that point of view, data flow ideas, and in some cases, functional languages ideas are thriving, right? So you can think at codexes, for example, H.264, or network applications like packet filtering, etc. OFDM protocols, right? Everything you use, whether it's 802.11 or 8.16 or whatever, all these things, baseband processing, people want special purpose hardware because power consumption is the highest level concern in this. Deep neural networks. In fact, this is one of the biggest surprises for me. In the last PLDI, not the most recent one, but the one that was in Barcelona, one of the keynotes was by Martin Abadi from Google, who's a Google fellow. And he suddenly is showing slides on data flow from our work from 80s. He's saying, we have come to realize that's the only formalism which is pure data flow. There is no separate control tokens running around, right? Everything is being expressed in terms of networks. And he says our networks have become large enough that mixing control and timing information is very, very tough. So we want to think of these deep neural networks in terms of compositions of asynchronous things, how they're going on. So he grilled me for 2 hours about how we were debugging and how did you know what was an error, and was the error unique? And many of these problems we had visited in the old days. So I'm kind of happy but surprised that what use it's finding in modern times. So this is just to make sure everybody understands what I'm talking about. They're talking about a higher level language, what should be the software view of TensorFlow chip they have. And they want to have a data flow like thing so that it's easy to compile, where they have enough control over, how it's going to map on their extremely wide data flow network. Everybody has heard of MapReduce, things, not the way we are talking about in this class, but I mean, again, when people are storing everything in files, right? You do maps on large things, and then you do. Why they have appeal there? Because they like the functional aspect. If something dies, if some mapping failed, right? Some element didn't do it, either the hardware failed, software failed, or just because it's taking too long, go and compute it again. Because they expect input file to output file transformation to be absolutely functional. So this has proved to be such a useful paradigm. It is widely adopted now for distributed processing. And then pretty soon you start hearing all the optimizations we used to talk about in 80s. Oh, if you do fusion, you can eliminate one file write, because you don't have to write it in file and then read it. If you can figure it out at the high level, then you can do fusion between two functions that are doing. So if you see the languages that are from which map and reduce and the way people are doing it in Spark, why Spark is better than something else, is again because lots of transformations that we were doing with functional languages in the early days are being done now. It's just the domain is different. Their input values are not small lists, they're whole files. Okay, but the idea works. So here I just thought I'll quickly show you 2 pictures. So one is, this is the decoder for H.264. Literally, if you open up a signal processing book, that's what you will see. They will not draw the cues in between, so I have just drawn them, right? But they literally think of each step as a mathematical transformation. You give me some value, it comes out here. You give me some value, And if you see hardware implementations of it, they do exactly the same thing, you know. If you see software implementation of it, you won't be able to recognize this picture. If you look at the code in Linux, you know, utility for H.264, because what happens there is, it's very expensive to copy, right? Because this is implying there is no shared storage between these things. So they worry a lot, you know, once they have read a frame, right? Let's do as much work as we can. So they don't think of it in a natural data flow fashion. They think in terms of, here is a frame, how far can I go in my sequence before I have to look at the next thing? So they have to deal with parallelism in that situation, but they are explicitly trying to optimize something, right? And that optimization is exactly the thing that gives us a headache when if we start out with that code and we want to parallelize it. The natural algorithm in that is absolutely what I've drawn here. So when we build hardware, this is what we start out with, and we can express it and do it exactly like that. There's some other thing which is very important when you start doing hardware design, and that is same codex applies, but the devices are so many, right? What is the size? You know, are you talking about 720 by 480, or are you talking about 1080 by 720? What is your frame rate, etc.? Again, if you are doing software, you don't have to worry about these things. You get whatever you get. If it's not fast enough, you say, go and buy a faster machine, right? But nobody is going to look at it and tune it for your particular machine. So only time in software when they start worrying about this is when they run it on your on your cell phone. And therefore they have special media processors, you know, which are being designed, you know, so that some of these kinds of codexes can run very, very fast. From hardware, software, whichever point of view you want to look at, you really would like to have specifications which can be done either in hardware or in software, right? And somebody has to specify the rate at which this computation has to be done, because that's the only way we can minimize power. Because if you want it very fast, it's going to take more power. Okay, so here is another example which I don't really expect you to read, but all modern protocols, that's too strong a statement. Most modern communication protocols are OFDM based. It has a very solid mathematical base, and they all have this diagram. Okay, so you have FFT, inverse FFT, interleaver, mapper, forward encoding, etc., etc. Right? And literally you can think of them as independent boxes which are communicating with each other in a latency insensitive manner. Now, if you look at this picture, what is very interesting is different algorithms, different codexes will, different baseband processing algorithms will use different algorithms here. So the block diagram remains the same, but this block will be completely different depending upon whether you're using convolutional codes or turbo code or Reed-Solomon code, etc. And they all have very different amount of computation. You can have reusable algorithms with different parameter settings. So a scrambler is really, it's the same algorithm if you're thinking from software point of view, but you just look at different bits in the incoming word. So here you're looking at 7th and 4th, here you're looking at 15th and 14th, etc. Now what is even more interesting is FFT, you say, I've done my FFT, leave me alone, right? The problem is different codexes have completely different requirements. Here you want to do 634 point FFT at 0.25 megahertz. 256 point FFT at 0.03 megahertz, very, very slow. Look at this one. In USB, you want to do 128 point FFT. And when you use such devices, the first question you ask is how little power it takes. Because if your radio in your cell phone was lousy, it'll immediately drain power, right? So there is no design which you can say is done in this game if somebody else can come and do it at a lower power and still maintain the speeds you want. So that's both an algorithmic thing, lots of challenges in that, and that's why special purpose hardware is so interesting. And you want methodology so that you can keep the same source description, but generate different hardware depending on what performance you want from it. Okay, so this is the point at which I'm going to echo what Keshav was saying earlier. There's a need to go beyond data flow. Data flow, like functional languages, obscure resource management issues which must be handled efficiently in any practical system. Yes, it's an elegant model. And believe me, once you have learned it, it never leaves you. Right? So Keshav can do whatever he wants. He still is going to do lambda calculus. He's still going to do data flow, right? Because they become part of you. It's just, you say, yeah, I know this. Let's move on, because he already takes that kind of thinking for granted, right? But there is a need to more control. There is a need for more control if efficiency of implementation is important. And look, ultimately computer science is about efficiency. We are looking for efficient algorithms. We are looking for efficient software. We're looking for efficient hardware in this. So you can never get away from efficiency concerns. Now, lack of shared state between nodes. So in all these models, regardless of what tricks I play underneath, right, that I may put a token somewhere and move the pointers to it from here to there, the basic model is that nodes have their own storage, or you don't share storage, because then all kinds of other problems will arise. And the moment you start out with a model like that, then some things just don't fit, right? I mean, if you want to think of the kind of graph algorithm Keshav is talking about, even based on what I've shown you, it's not going to get you very far, because you already have a graph, right? You're computing on it, right? So it's a question of how to express those computations, and that requires a different way of thinking. And final point, which is perhaps the most important one, is determinacy. Though it's highly desirable in many situations, we all love Church-Rosser theorem. We all love the idea that how Gilles Khan showed us, we can think about as a solution, least fixed point solution to recursive equations. But the problem is, it's very limiting in many situations. It's very limiting, at least for specification. Even if your answers in some situations are unique, you may still want some flexibility in how you specify the problem. Let me give you a problem from my world, which is I live in the world of hardware and computer design and so on, right? All modern processors are speculative. So, we guess, your branches are going to resolve in this way, and we can run really ahead. I mean, as much as 100 instructions ahead before the branch is resolved. You would not want a specification or an implementation method where you say, I want you to speculate 50. What kind of specification would that be, right? So when you speculate, you build a system, which may say, well, on the wrong path instruction, kill the wrong path instruction. It will not be acceptable to forcefully make it deterministic by saying, on the wrong path, you can only have these 5 instructions. So many of such things, I'm giving you that example because ISA semantics are deterministic. But the level at which we deal with it is a microarchitecture, right? And we need tools to deal with that non-determinacy. We need tools which will preserve some other specification for many of those things, because ISA level specs will be way too high level than what we are working. So what I'm going to do in the next 2 lectures is actually present you an alternative model, right? So it's also about serializable atomic transactions, which you've heard about. Galois has it also, and many other things have it. So these ideas are all floating in air these days. Database people, of course, have had it forever. It's just that I will use it in a very particular fashion. And in my world, all the other concurrency models I want to build, I get in this kind of thing I'll show you. And the reason I'm interested in is guard atomic action is also even able to efficient hardware implementations. So you're going to get some lessons in hardware in the next 2 lectures that we can at the same time talk at very, very high level, because I'm actually going to do some semantics for this kind of a language. But at the same time convince you I really do know how to generate hardware from it. Efficient hardware. When I say generate hardware, it's not that I can generate hardware. You can do no better by rolling up your sleeves and coding at a lower level. Okay, so we'll stop here. So these slides are on the website. And I also tried to prepare a bibliography for Dataflow, which I gave up immediately. So I've just listed the papers which have my name in them. So they stop around 1995, right? Because that's the last time I wrote a paper on Dataflow. But if you follow the pointers, I mean, if you read those papers, then you'll find the whole extensive bibliography, which somewhere I must have, but I couldn't find it now. And all the students used to work on these things. They have become way too important. They're professors in big institutions. I can't call them up. He says, hey, do you have the Dataflow bibliography? He said, what? That I left with you. So it's there. And I think there is enough information there if you want, you can reconstruct it. Very good. Thank you.